We are presenting our AI-powered virtual reality system designed to train patients with upper limb amputations or with congenital defects and prepare them for controlling bionic prosthesis with a large number of degrees of freedom by decoding the patient's electromyographic activity. Individuals who have undergone upper limb amputation or have congenital absence of the limb encounter significant challenges in their daily lives when performing routine activities. Although currently available bionic prosthesis solutions offer some help, their usage among amputees is limited and more than 60% of patients decide not to use them. Control systems of the commercially available wrist prosthetic devices are still primitive and typically use discrete binary decoding of extensor and flexor muscles activity to choose between a pair of externally enabled grip patterns. The extended repertoire of grips and gestures is implemented by means of manually switched modes, typically accomplished with the help of the healthy limb. More sophisticated decoding solutions are needed in order to support prosthetic devices with a large number of degrees of freedom, with preferably continuous decoding of patients' residual muscular activity. Both decoder and the user need to adapt to each other so that the decoder could learn to accurately interpret the patterns of electromyographic activity generated by the patient. To facilitate this process, we have developed a novel AI-powered virtual reality system for teaching real patients with amputation, both acquired and congenital, to use a prosthesis with a high number of degrees of freedom. Our system comprises a virtual reality environment combined with a pre-trained neural network decoder used to convert a patient's movement intentions into the kinematics of the virtual limb. We mirror the healthy hand in VR while recording its kinematics and EMG of residual muscles at the same time. The main task for the participant is to move both hands in parallel, since we use movements of the healthy hand as the target to fine-tune our model to the particular patient. Our machine learning solution is a neural network with convolutional layers and a decoder-encoder architecture with 4 million parameters. The output of the network is a 64-element vector containing quaternions for 16 joints. We use models pre-trained on healthy subjects to improve performance and fine-tune the pre-trained network, first offline using collected data from a new incoming patient, and then fine-tuning it online while interacting with our VR system. It's especially challenging to work with patients suffering from congenital structural defects of the limbs, who have not developed the proper muscular control mechanisms. We experimented with participants with congenital hyperplasia, who wear one grip prosthesis every day. We have collected the data from 8 electrodes located around the forearm, combined with the kinematics of the healthy hand. Participants have taken part in the 3 stages of training over the course of 3 months, with different tasks to differentiate separate fingers, pinch with the thumb, and make gestures. Importantly, to train these patients in using our virtual wrist prosthetics, we did not employ any direct instructions during the training, so the participants have to choose the way to contract their muscles themselves. In total, we collected around 10 hours of data for every person. The training, which includes adaptation of both the patient and the machine learning model, results in patient's ability to exert continuous finger-specific control over all 5 fingers in real time. It is important to realize that in both of our patients, the thumb finger was somewhat developed while the rest of the fingers appeared to be nearly with no muscular control machinery developed. Numerically, the accuracy of predictions can be described as follows. We found that the model performs well, furnishing 7 degrees of error across different movements, and provides 0.8 correlation coefficient between the target kinematics read of the healthy limb and the kinematics of virtual prosthesis decoded from the muscular activity of the limb with hyperplasia. We have developed an AI-powered VR system for teaching amputees or congenital hyperplasia patients to use bionic prosthesis with natural control and a large number of degrees of freedom. Based on surface electromyogram only, our model can reconstruct kinematics with high accuracy invariant to the limb orientation. This became possible thanks to the mutual adaptation between the patient and the machine learning model that was enabled by the use of the pre-trained electromyogram decoding model to provide consistent outputs during the early stage of interacting with patients. The patients enjoy the experience, which means that the developed system may also positively influence the mood of amputees, make them not lose their residual muscles, and prepare them for the use of advanced prosthetic devices.
Hello, I have been using prosthesis every day for 6 years. It helps me to adapt to social life and perform physical activities. However, I would like more than just one grip. That's why I'm training to be able to use new technologies with more freedom of movement.